Okay, so next up we have Colin, Orion, Chandler, who's going to be talking about comets in Rubin, citizen science and interesting objects. All right, take it away whenever you're ready.
Can you hear me okay in the back? That looks like a blank face. Is this working?
Do you want to just tap? Tap on. Yeah,
Okay.
it's fine.
Hopefully they can hear me. All right.
Yep. Me too.
Great. Well, hello again. I'm Colin Ryan Chandler, project scientist for the LSST Interdisciplinary Network for Collaboration and Computing, or LINC frameworks at the University of Washington and Jack Institute, where I'm a postdoc. I'm going to talk to you today about comets in Rubin. Thanks, Henry, for saving me so much time because I have too many slides. We said interesting objects because I wasn't allowed to say interstellar time. We work under these like weird cloak and dagger things sometimes, but it's really an interstellar object, which we've also heard about some. We just heard from Henry, we like volatiles in context where they tell us about not only life in our solar system, but elsewhere as we understand it. And then also he mentioned the awesome sort of second fiddle, in my opinion. People don't often talk about astrophysical processes like the DART impactor shown here for planetary defense is really important, but also like the Geminid meteor stream, its parent is Phaeton, for example. And there's some really awesome stuff we learned. And we heard this week about rotational disruption and creation of binaries, which I thought was really awesome. So the issue with these active small bodies, which Henry also talked about, is that there's just not that many of them. Despite being known throughout history, these objects are actually kind of rare compared to asteroids. So there's just a few thousand comets, depending on how you count, and over 1.4 million asteroids, with many more on the way with Rubin. And of these special populations like active asteroids, there's just like 60 of them known. And that's since 1975. It does make me really happy. There's a glass plate that was actually scanned, so the first one was captured this way. But this just goes to show that they're quite rare. So an obvious solution: find more. And where we look, of course, we're looking at Rubin. Got it right on my shirt. But this is the field of view for context. We've seen this before from Mario, and just to say that it's a large aperture telescope with a large field of view, and so that combination is awesome for finding a bunch of objects at the same time, observing them at the same time, and seeing things that are really faint. So those are both kind of unprecedented. It's also a well-calibrated data set, and it's going to be nicely curated, and it's in commissioning now, so there's actually data. For the citizen science I'm going to talk about in terms of our project right now, it's with this subset from what's called the commissioning camera. That's just one, it's a camera that has single RAF, so 9 chips instead of the 22 RAF, so it's 1/22 of the data in an image. And this was data collected in 2024, as opposed to the big camera is what we call it, and that's been going since April, as we heard from Mario. So the main point is just that this is a small finite subset, so we treat this a little bit differently than we would with some other data sets. There are a handful of actual big camera images in there in the project because of Atlas, and we'll come back to that. So we already saw this movie, but I'll just like a couple random commentaries because my perspective is maybe a little different. I just want to remind that Rubin is going to find a lot of these objects. Here's one that's moving in front of a galaxy. This is a recurring problem for us. So yeah, I know it's a really positive video, but I'm going to say a few caveats. And another obvious caveat is there's just a ton of these dots. And so just in a week, we found 2,500 new objects, and we haven't even told people yet how many observations we have of known objects in there. It's just a lot. And so it's an overwhelming data set. The average is 300,000 observations per night. And we would like to look and see of these things, do they have tails? It's too many for me to look at. And so just putting this in context, it's a common problem, not just in our field. And so citizen science is one way you can address these sort of huge needle in a haystack type problems. It is also extra prescient right now. I mean, I'm excited about it because it engages the public in scientific endeavors. And that happens to be extra relevant for us right now in terms of communicating science to the public, et cetera. But it does actually accomplish tasks and gets people involved, and it's very exciting. I mentioned some of these numbers already, but there is less examination bias. Like I get to swallow my pride and say that I have volunteers, like a Kaiser Permanente medical doctor from Napa, they're better at finding activity than I am, despite me having looked at zillions and zillions of these things and getting a PhD in looking at thumbnails. And so that leads to less bias. And so when you're talking about not just the science that we're doing, but also the AI training to sort of help in this process going forward because of the scales, it's really important. So this is a proven concept. I launched another citizen science project in 2021 that we're really proud of. It's discovered dozens of objects already to be active. There's an active centaur. There's some of these active asteroids and maybe comet candidates we heard Henry talk about. The point of this slide is just to say this is not like a pie in the sky idea. It's already proven. We've shown it's doable from the project side and that volunteers can see activity. So the workflow is a little bit different for Rubin comet catchers than before, just for many reasons. The basic idea is we've got the field, we figure out what was in it, we pull a chip with our friendly butler, that's a Rubin thing. We do a big cutout and then we rotate it because Rubin is not celestial coordinate aligned in its imaging. And then we do CSI enhance and we get beautiful cutouts, which we take and put into flipbooks like this. This is also new for us, with the idea being that if there's a galaxy in the background that's moving, people can more easily tell, like that's not actually from the asteroid. This is the whole interface. It's just a yes or no question. It's that simple. So I mentioned AI earlier. We have this prototype. We like to call it prototype because this is how AI people are. And it's called TailNet. And it is trained on no data. So everybody says no all the time because this is a rare phenomenon. And so the point I try to get across is that it is very good at saying this is definitely not active. So it's a bit confusing, but it has led to 5 discoveries so far. It's the only AI that I'm aware of that has discovered 2 active asteroids and minimal comet candidates. It discovered active NEO recently and some other stuff, and that's really cool. And we're working on a paper to talk about this more. And of course, we are going to need stuff like this for Rubin. And we use this to enhance the volunteer experience, really. So this is filtering out junk, although not too much junk because empty images are boring to look at. The overall workflow is just like this. So we have Rubin. It takes data. In that telescope is not where it lives, but the Rubin Science Platform is how we've been accessing all of the data. We have this AI filtering. People classify stuff. There's forums where people talk about it. That is where we made our first discoveries with the prior project, so we anticipate that will happen again. We analyze this stuff, do follow-up with telescopes and archival investigations, and science, which we know looks like programming. All right, so let's talk about 3i just for a moment. So this is something that happened with Rubin I'm excited about. And so we saw this thing in archival data. It's great that we get these free deliveries from probably other solar systems, although as Renu mentioned, it could be also a self-delivery with a time capsule. This was our aha moment at the left. This hasn't been shown before. This is when we realized, or I realized we actually have images of it, and so we could pursue this. Just for context, it was one day after Rubin Comet Catchers went live, one day after Data Preview 1 was released to the public. It was not the best timing for us in so many ways, but it's great. I'm not going to look this gift horse in the mouth. We learned a lot. I mean, I'm on the commissioning team, and so in the commissioning hat, this has been a really important endeavor. So they said maybe we could tip the telescope a couple degrees. We got to do spherical aberration, something optics that I don't understand. Yeah, that'd be great if that works for you. And so we do have a lot of additional images, like over 100 additional images scattered through some weeks. We did a bunch of target of opportunity testing for them. So I'm going to take credit for the gravity wave that happened a couple weeks later, how well that went off. My student Devanshi made this tool to show where objects are for the planning team. And then just to be really obscene, we have a minimum stack here where we take the minimum value of each pixel because we have just so much in the way of photons that we can get away with sort of neat party tricks like this and do some new science. This is just some other features that we had. There's a declination offset that everyone keeps asking me about, and that's mostly been dialed in, but it's really crucial that we get these things in top shape for Rubin. This is showing our modeling of where the observations are going to happen and how this is lined up with the interstellar object, and this is leading to us to hope that we're going to get on the order of maybe 50 interstellar comets if we're optimistic. There's more I don't want to say about deep blending. The more exciting thing is just this big collaboration between the entire solar system science collaboration, all of Rubin project, and all of the people with Rubin builder status, and that has been an awesome endeavor, although difficult. But it's been, I think, a really nice example of cooperation that we can do in our field. And so with that, I'm going to leave my summary slide up here just to say we've had a ton of participation. We're the first Rubin Citizen Science project. We've got the first Rubin science paper out, which is, if you'd asked me 3 years ago if I thought I'd be doing that, I would have said you're crazy. And so I'm happy to be doing this. There's the results. Thanks.
All right, do we have any questions? Got a couple down here. I also want to encourage any early career researchers, please do ask questions as well.
Can you tell us more about the active near-Earth asteroid?
Yeah, you mean this one? No. I can't. And there's a no picture slide, but you can take pictures. It doesn't matter anymore. And I'd rather go on YouTube or wherever this is going instead of not. This one was. I'm trying to remember if this was the case. Yeah, this is one where I was teaching a student how to do this, and it was fun. I did this Google search. There's like a Facebook post in Russian from 2004, and it turns out Borisov observed it once, but didn't care because he couldn't get naming rights. It's a long story, but it's an interesting object, as well as a case study in how we can find things that maybe have not been recognized as comets, but we can add to that the data set enough to be able to have it classified as one. Yeah, but it's 2012 DG61. It's out there.
Got time for one more question, so just over here.
Yeah, I'm curious about your machine learning technique. Do you have any estimate of what the false negative rate might be? And do you have any sort of like injecting, fake synthetic data for testing?
That's a great question. False negative of something that says, no, it's not inactive. So that's 4 negatives in a row. But anyway, so we use for this case, because there unfortunately have not been comets that we've seen so far in the DP1 data set. We have the DECAM training data that we prepared, as well as negative training. So positive that definitely show comets and then negative that don't. And that's what we're compiling. And it's, I think between the two projects, we're something like 5 million data points so far.
All right, let's thank our speaker again.
Mm-hmm.
And if you have additional questions, please feel free to post them on the Slack.